Now, here's some real practical information that you actually need to conduct today's lab. And I'm going to go over this. Hopefully, you have spent some time looking at it and have made sense of it, but I'm hopefully going to clear up any gaps here as well. So you're asked to prepare, in this lab, you're asked to prepare 3 buffers, and that's part of the preparation. You do this before you start actually executing the different activities. And you're asked to determine the volumes of 0.1 molar acetic acid and 0.1 molar sodium acetate required to prepare 10 mils, so you have a known volume, of the following pH buffers. And it gives you the example of 3.7, and then it asks you to do 4.7 and 5.7. So this is the example that's worked in the investigation manual. You start with the Henderson-Hasselbalch equation, pH is equal to pKa, log of the conjugate base over the acid. Now I've been using HA and A minus as generic placeholders for the acid and the conjugate base. In the terminology of the investigation manual, they're using base and acid, or B and A, as the same generic placeholders rather than writing out acetic acid. Let's see, CH3, COOH. CH3, COO minus. They're saying this is rather acid, or A. So these 4 terms are all equivalent. What's a little confusing, and I apologize for this, I'm just realizing this as I'm doing this, is that the A that they use, don't confuse that with A minus. A minus is the conjugate base. When they want to talk about the conjugate base, they're just using the word base or the letter B. But these terms here are all equivalent. This is a generic placeholder. This is a generic placeholder. This is a generic placeholder. This is the specific conjugate base that we're using with acetic acid and sodium acetate. So again, generic expressions, basically a variable, and then this is where the variable is given a more specific name. But we set up our Henderson-Hasselbalch equation, and we're told in the worked example that the pH is 3.7. That's the buffer we want. So we put 3.7 in the expression. We're given the pKa of acetic acid is 4.7. So we put that in the expression. So pH is equal to pKa plus the log of this ratio. Now, we can simplify this by adding negative 4.7 to both sides of the equation. So if we add negative 4.7 here, this becomes 0, drops out. If we add negative 4.7 here, that simplifies to minus 1. Negative 4.7 and 3.7 is negative 1. So negative 1 is equal to this log of this ratio. We take the inverse log, so that's the same as saying 10 raised to the power of negative 1 is equal to it's the inverse log, so that gets rid of the log term, so concentration of the base over concentration of the acid. 10 raised to the power of minus 1 is 0.1. And then we can multiply both sides, so you get the 0.1 here. If we multiply both sides by A, in brackets, the concentration of the acid, then this becomes, the A cancels on the left and ends up in the numerator, the top of the expression on the right-hand side. So the concentration of base is equal to 0.10 times the concentration of acid. So this tells us the base is 10 times greater than the concentration. No, sorry. The base is 10 times less than the concentration of the acid. The acid times 0.1 gives us the concentration of the base. So most people have no trouble getting to this point, or have little trouble getting to this point. Where the confusion comes up is, where does this come from? And what I found is that most people are able to take this and solve for the other pHs, 4.7 and 5.7, but sometimes understanding where this comes from is a little confusing. So I'm going to take a second to explain this. In the case where we know the volume we're making, or if we assume there's a fixed volume, and the buffer is made by two solutions of the same concentration, 0.1, containing the same counterion, acetate, then you can use this simplifying assumption of A plus B equals 1. So where does this come from? If I have acid, acetic acid, I have acetate, and this is 0.1 molar, and this one's 0.1 molar, and then buffer concentration. When we talk about the buffer concentration, we talk about the conjugate base concentration. So this is a 10th molar concentration of 10th molar acetate buffer. So 0.1 molar. If I have 0 mils of acetic acid and 10 mils, 0 mils of 0.1 molar acetic acid and 10 mils of 0.1 molar acetate, I have, it's not a buffer because I'm outside of the working range, but excuse that for a moment. My concentration is 0.1 molar in acetate. If I have 10 mils of acetic acid and 0 mils of the sodium acetate, my solution is still 0.1 molar in acetate. And if I have 50-50, 5 mils, 5 mils, my final concentration is still 0.1 molar in acetate. So what does this tell me? It tells me that the parts are always equal to the sum. The sum is always 1, and the two parts always equal 1, and that's what this expression is telling me, that A plus B always equals 1, and that's because these are the same concentration. So this is a simplifying assumption that works in this case. If these two were not the same concentration, you could not use this. So because the parts always equal the sum, because everything's the same concentration, we can rearrange this and say that we can take this expression, that the value of B is really 0.10A, and we can put that in here. We can replace this B with that number. So this 0.10A is now here. And now we have an equation with one unknown. We can solve for this. So 1.1A equals 1. And see, I would have written this as 100 rather than 1. But for every 0.91 milliliters of A, you have 0.09 milliliters of B, and you need 10 mils. So you're just going to multiply this by 10, and you're going to get 9.1 milliliters of acetic acid and 0.9 of sodium acetate. And then my total volume is going to be my 10 mils, which is what I wanted. So that's where this comes from. This is a simplifying assumption. It doesn't apply in all cases. It applies when the weak acid and the weak base are prepared at the same concentration. So I think I have the same information here on the slides broken out in a little more with a little more space. So we have our Henderson-Hasselbalch equation. We have 3 buffers we're going to prepare, and we know the pKa of our buffer. So we set up our Henderson-Hasselbalch equation. We fill in the pKa because we're given that. We have 3 different pH values that we're going to fill in here. So I've done that. So in the case of pH 3.7, we just worked that example on the previous slide. In the case of pH 4.7, we're going to add negative 4.7 to both sides. So negative 4.7 equals log, and then that's going to cancel, and that's going to give us this. And the log of 1 is the log of 1 is 0. And then we're going to say 10. Sorry, confused myself a little bit. We're starting off with a pH of 4.7. So 4.7 minus 4.7 is 0. So 0 equals the log of acetate over acetic acid. Oh, sorry, let me fix that. And we recall that when this is 1, this is 0. So the two concentrations, the two amounts are the same. So 2 volumes of the same, 2 identical volumes of the identical concentration. So 5 mils and 5 mils will give us this one. Let me show you these worked out with a little more organization. So in the case of 3.7, the log ratio is minus 1. In the case of 4.7, the log ratio is 0. In the case of 5.7, the log ratio is 1. So this is our pH value plus or minus 1 pH unit to give us our working range. And then when we solve these expressions,